You stand in absolute darkness. You press your thumb forward, hear a sharp click, and instantly a beam of white light cuts through the room. To get that exact same effect in a house, we rely on a massive, continent-spanning grid. Thick, heavy cables suspended from steel transmission towers move alternating current across hundreds of miles of open landscape. And all those wires trace back to sprawling facilities, thermal, hydro, or nuclear power plants, where giant turbines generate the electricity required to light up cities. Yet we can hold that exact same capability in the palm of our hands. A simple, classic metal flashlight bypasses the need for cooling towers and high-tension wires entirely. Electricity is, at its core, a flow of energy. To make it do actual work, like illuminating a dark space, that flow simply needs to be contained, pressurized, and directed through specific components. The process starts with the electric cells inside the casing. These cylinders hold stored chemical energy, sealed up and waiting to be released as a direct current. Think of this energy like water sitting in a pipe. To get it to move, you need pressure. In an electrical system, that push is called voltage. Look at the ends of the cell. One side is a flat metal disc, and the other is a protruding metal cap. These are the negative and positive terminals, establishing the direction the energy wants to flow. When you slide them into a flashlight head to tail, connecting the positive terminal of one to the negative terminal of the next, you create a series connection. This arrangement effectively doubles the total push, or voltage, driving the current. If you were to place those same cells side by side, creating a parallel connection, the voltage stays exactly the same. Instead, the capacity increases. It is like adding a second lane to a highway. The cars don't move any faster, but the traffic flows for a lot longer. But regardless of the layout, if you put a cell in backward, the push goes in the wrong direction. The internal flow is interrupted and the device stays dead. For the device to work, the electricity needs a continuous, unbroken path to travel from the positive terminal, through the bulb, and back to the negative terminal. This complete loop is called an electric circuit. Engineers map these pathways using standard schematic symbols. The battery becomes a set of parallel lines, the wire a straight line, and the bulb a circle with a cross inside it. But an unbroken loop would mean the flashlight is always on. To control the flow, we introduce a switch, a manual drawbridge for the electrical highway. Push the button, the bridge drops, and you have a closed circuit. The current flows. Click it again, the bridge lifts, creating an open circuit, and the electricity stops instantly. All the stored chemical energy in those batteries does absolutely nothing until human interaction physically bridges that gap. Once the circuit is closed, the current slams into the bulb. In an older, incandescent flashlight, the electricity is forced through a thin wire made of tungsten, called a filament. The resistance is so high that the metal heats up until it glows white hot. Modern flashlights skip that extreme heat. They use light-emitting diodes, or LEDs, which pass the current through a semiconductor to produce light with very little wasted temperature. But an LED is a strictly one-way street. The current must enter through the longer, positive leg, and exit through the shorter, negative leg. If the flow hits it from the wrong direction, the diode blocks it entirely. To make sure the current glides effortlessly from the battery to that LED, the internal pathways are built from conductors. Metals like copper, aluminum, and brass act as open superhighways for the electrons. Surrounding those highways are insulators, materials like rubber, plastic, and glass. They lack free electrons, meaning they act as impenetrable walls, blocking the current from escaping its designated path. Controlling electricity requires this exact architectural balance: conductors to guide the immense power forward, and insulators to trap it tightly inside the wires. That physical boundary is critical because our bodies are mostly water, and water, especially with minerals in it, makes human skin and tissue highly effective conductors of electricity. If you handle an electrical device with wet hands, the water bridges the gap over the plastic insulators. It invites the current to leave the circuit and take a new, dangerous path directly through you. This is exactly why damaged cords and exposed wires are severe hazards. A broken insulator releases the raw electrical push into the surrounding environment, creating a massive risk of fire or injury. So, when you stand in a dark room and slide a plastic switch forward, you are interacting directly with the physical laws of the universe. The darkness breaking into light is a perfectly engineered orchestration of chemistry, mapped pathways, and precisely chosen materials, all working flawlessly in the palm of your hand.